Welcome to lecture 3. Last time we introduced probability models. Does anybody have any very important questions from last time? Okay, so the last time, let's quickly review. The elements of a probability model are, there's an experiment, there is a set of outcomes which is called the sample space, and there is a probability law. Okay? Probability law is what? It's a mapping from sets that are subsets of the sample space. We call them events. It's a mapping from events to numbers. Okay? P of A is the probability of the set A. And according to our probability, applied probability class, as you know, it's all built on 3 axioms. So probabilities have to satisfy 3 axioms. They are, well, probabilities are always non-negative, larger or equal to 0. They are additive. The probability of the union of 2 events that are disjoint is the sum of the probabilities of those events. And finally, we have a normalization axiom, which is the probability of the whole sample space is set to 1. And that implies that probabilities are always between 0 and 1. Okay. So the topic of today is discrete probability models. Last time we saw examples where the sample space was contained a finite number of outcomes, or a countably infinite number of outcomes, or a continuum of outcomes, uncountably infinite number of outcomes. Okay? So the topic of the day is discrete probability models. A discrete probability model has a sample space which is countable. Has either a finite number of elements or an infinite, countably infinite number of elements. Okay? The simplest example is toss one coin. So I guess at this point I can give you the lecture notes for today. So if you toss a fair coin, the model is the probability of heads is something and the probability of tails is something else. Those are the 2 outcomes, heads or tails. Let's say the probability of heads, probability of getting the outcome heads is P. Okay? Probability of heads plus the probability of tails should be what? Should be 1. Why? Because heads and tails are the only outcomes, and together they make up the sample space and they are disjoint. So by additivity and normalization, this is 1. So then the probability of tails is what? 1 minus P, right? Now, if the coin is fair, if the coin is so-called fair, fair coin, where is this? Then the probabilities of the outcomes are equal. In other words, they are both 1/2. Okay? This is, later on. Anyway, let's not digress at this point. So in general, in a discrete probability model, the probability of any event, which is composed of the outcomes S1, S sub 2 through S sub k, is the sum of the probabilities of its individual elements. Okay? Because we can, since it's a countable set, we can associate probabilities with individual elements, and by the additivity axiom, the sum of the probability of the whole set is the sum of the probabilities of the individual elements. Okay? So, example. Let's throw a 6-sided die. Okay? What's a die? Let me try to draw it for you. So, 6-sided die. Let me try my best for drawing this. Well, there are dots on the faces, right? I don't know if an actual die looks like this, but every face has a number, and the probabilities of these faces may or may not be equal. Okay, there are numbers 1 through 6. Let's express the probability of the outcome, probability that the outcome is 1 or 6. Okay? The probability of the event, I get 1 or 6. What is this? This is the probability of the set Emre. Where's Emre? Emre, what is the probability of this, this set?
1 and 6.
Exactly. 1 or 6, right? And by additivity, I can write this as the probability of 1 plus the probability of 6. Right? Okay. Now, if the probability law is uniform, this means all the outcomes are equally probable. Okay? So, uniform means equally probable. If the sample space consists of n outcomes, which are equally likely, then you can find the probability of an event by counting the number of outcomes in that event and dividing it by the total number of possible outcomes. Okay? I said counting. Okay? So we will need to know how to count in this course. Okay? What is the branch of mathematics that deals with counting? Combinatorics, right. So we will do a brief lecture on combinatorics. So we know exactly how to count. So this becomes, this occurs a lot. A uniform probability law occurs a lot in a lot of models, as well as modeling real life. Example, let the faces of the die be equally probable. Right? What's your name, please? Yes. Ahmed. So can you apply the uniform probability law to the die example?
Yes.
Go ahead. So if the probability law was uniform, Ahmed, then
1 over 3.
the probability of every, exactly, the probability of every face is equal, and they are 1 over 6. In other words, the probability of the event 1 or 6 is the size of the event 1 or 6 divided by the size of the sample space, which is 2 over 6. Any questions? No questions? Okay. Think about the next example. A fair coin is tossed until tails is observed. We talked about this case last time. And what did we have for this case? The sample space is countably infinite. Now, let's determine the probabilities of each outcome in this sample space. What do you think? Let's see. For this, we could use a sequential description. Excuse me? Right, maybe, except we don't know anything about independence yet, so we can't multiply. So in the first toss, I get either heads or tails. If I get heads, I'm done. What is the probability of this event? 1/2. It's fair coin. With probability 1/2, I'm sorry, I'm tossing until a tails is observed. So if I get tails, I'm done. If I get heads, I will continue. Now, if I get heads, again, I'll toss the coin. And with probability 1/2, it's tails, and I stop. With probability 1/2, it's heads, and I continue. Okay, so what is the weight of this branch? It's 1/2. Okay, so the probability of the outcome tails is 1/2. What's the weight of this whole branch, which contains an infinite number of outcomes? That's also 1/2. Okay, now you can show that the probability of the outcome HHT such that the length of the sequence is n is 1 minus, well, let's see. P is the probability of getting heads, and 1 minus P is the probability of getting tails. So 1 minus P times P to the n minus 1. How can you show this? Well, we don't know independence yet, but you can sum this sequence and show that it adds up to 1/2 on this branch, and we'll revisit this later. This will be called the geometric distribution. Anyway, let's move on. Okay, here's an example, simple example, very fundamental example. There's a file that contains 1 kilobytes of data. What is 1 kilobytes? How many bytes is that? 1,000 bytes. Now, the probability that there exists at least one corrupted byte, at least one byte in error, is 0.01. The probability that there are at least 2 corrupted bytes is 0.005. Okay? Let the outcome of the experiment be the number of bytes that are in error. So what is the sample space in this case? The sample space contains exactly numbers. So let's try this. The sample space is the numbers, integers, from 0 up to 1,000. Okay, because the outcome is the number of bytes that are in error. This means 0 means no bytes in error. 1,000 means all the bytes are in error. Okay, that's the sample space, part A. What is the probability that there are no errors? How do we, huh?
99.9.
How did you get that?
1 minus 1, 0.0.
Right. The event no errors is the event, the outcome being 0. Right? Which is what? Sample space difference, this set. The probability of the sample space difference 1 to up to 1,000. What is this set? At least one error. Okay? Okay. Now, this difference has the probability 1 minus the probability of, in other words, the event, no errors, is the complement of the event, at least one error, right? Right? So this event is the complement of the event, at least one error. So the probability of this event is 1 minus the probability that there's at least one error. Okay? Is there any question about that? So sometimes, if we don't know the probability of an event directly, but we're given the probability of the complement of the event, the probability that that event does not happen, we simply can find the probability of the event by subtracting from 1 the probability of the complement. Okay. Is this clear? Is this clear? Okay. So what's the next question? What is the probability that there's exactly 1 byte in error? Exactly 1. How do we do that? Probability of exactly 1 byte in error. How did you do that? What's your name, please? Eli. Eli.
We divide 1 byte by total events, number of total possible events.
But we, okay, interesting. But we're not given that this is a uniform probability law. We are not given here that the uniform probability law is valid. Okay? If we knew that all these outcomes were equally likely, then what you said would have been correct. But we're not given that. We're only given that, we're only given the probability that there's at least 1 error and the probability that there's at least 2 errors. Okay? So, yes, please.
0.005.
I don't know the number. Tell me how you got it.
There's no 0.01 is the total number of errors, which are 1 error, 2 error to 1,000 error.
Right.
If we I say, and we know 0.005 is the 2, 3.
Right. I see what you mean. So here's what he's doing. He says, let A be the event that there's at least one error. Okay? And let B be the event that there are at least 2 errors. Okay? What's the relationship between A and B? Is A a subset of B or B a subset of A? B is a subset of A. Why? Because if there are at least 2 errors, then there's at least 1 error. B is inside A. If B happens, A happens. Okay? If A happens, B does not necessarily happen because there is at least 1 outcome here, which is 1. Okay? Now, then, we can write the probability of A as the probability of B plus the probability of B difference A. Right? Are these disjoint? Yes. B and B difference A. Oh, no. B and A difference B. B and A difference B. By definition, they are disjoint sets. Okay? So what is the probability of B? Are we given the probability of B? Yes. It's what? 0.005. 0.005. What's the probability of A? 0.01. Yes. 0.01. So this tells me that the probability of A difference B is 0.005. But A difference B is exactly the outcome 1 itself. Okay? So in other words, the event that there is one or more errors is the union of the events 2 or more errors and the event 1 error only. Okay? So I can subtract from 1 or more the probability of 2 or more to get the probability of exactly 1. Okay. Any questions? Let's move on. What's the probability that there is at most 1 byte is in error? We knew the probability that there is at least 1. Now, what is the probability that there is at most 1? Yes, please.
1 minus at least 2.
Ah, interesting. 1 minus at least 2 would give us at most 1. That's good. Part D. So 1 minus the probability of at least 2 would give us at most 1. Does everybody agree? Okay. So what is that? 1 minus at least 2. At least 2 is 0.005, which is 0.995. Is there another way that you can think of? There are usually more than one way to do a probability, to answer a probability problem.
No errors.
Yes, please.
Probability of no errors
Plus
plus
exactly 1 error. Right. So let me write that down. Probability of at most 1 error. In other words, the probability of 0 or 1 errors is the sum of P of 0 plus P of 1. Why? Because this is a discrete sample space, discrete probability law. We already know that probability of 0, we computed that. What was it? I guess I never wrote it down. 1 minus 0.01, right? 1 minus 0.01, I guess, right? 0.99 plus the probability of exactly 1. 0, where is that? Here. 0.005. So 0.995. We got the same answer as this, as expected. Any questions? Is this clear? Can you read this at the back? No? What would you need? Is there anything we can improve this the situation? Excuse me? This line, it's too low. The slide. Maybe we can turn the light off here? Don't think it will help? Zoom it in? Okay. Let's also try this. Is this better? Maybe. Okay. So that's the end of our discussion on discrete probability models. Now we can switch to continuous probability models, and let me try to zoom in. Oops. Okay. Is it better? Okay. So, continuous model. In this case, the sample space is an uncountable set. Okay. How do we compute the probability when the sample space is uncountable? This time we can't count anymore. Okay. So what we do is we usually measure a set by its weight, probability weight, loosely defined. This could be the area that represented by the set in proportion to the whole area of the sample space, etc. It'll be clear when we look at examples. So here's the example. I start driving to work in the morning at some time uniformly chosen in the interval 8:30 to 9. Okay, so uniformly chosen. What does this mean, do you think? The time is uniformly chosen. Let's suppose this is a timeline. This is 8:30 and this is 9. Okay. My start time for traveling to work is uniformly chosen in this interval. This means every point in this interval is equally likely. This is what people imply when they sometimes say, I choose a point at random. What they mean is I choose a point uniformly at random and every point is equally probable. But when every point is equally probable, there's a problem. If you associate a non-zero probability for every point, since there's an uncountable number of points, the probability of the sum does not add to 1. Okay? In this case, in fact, every individual point, which is a real number, has probability exactly 0. Okay? But the probabilities of intervals are finite. Okay, so let's answer a very simple question about this. What is the probability that my start time is in the interval 8:30 to 8:45? What is this interval? This is the first half of this whole time interval. Okay? It is certain that I will set out sometime from 8:30 to 9. What is the likelihood that I set out in the first half? What? It's pretty obvious, right? 1/2. This is 1/2. How did I measure this? I measured the length of this interval in proportion to the whole sample space. In this case, what is the sample space? The sample space is real numbers in this interval. Okay? If you want x such that, well, x is a real number, okay, such that x is between, well, let's say 0 to 30 minutes. Okay? And the desired event, we can name this as 0 and this is 30 minutes. Desired event is the event that x is between 0 and 15. Okay? Any question? Okay. So here's the big question now. This was a warm-up question. The interesting question is, let's see. Okay, my favorite radio program comes on at 8:30. Okay? My favorite radio program starts exactly at 8:30. And it may last anywhere from 5 minutes to 15 minutes. What is random? The duration of the radio program is random. Okay, it's not fixed, it's not deterministic, it's random. What is the probability that I catch at least part of the show, even if it's for just one brief moment? What is the probability that I catch at least part of the show? How can we think about this? Excuse me? Right. I will suggest that we define and we think about this in a two-dimensional way. Okay? Because right now, there are two things that are random. My start time is random, and the duration of the program is random. Okay, so there are two things that are random, and we are wondering something about the relation between these two things. Okay, so let x be my start time for driving. Okay, let y be the how about ending time of the show? Ending time of the show, the program. Okay, what is the event that I catch at least part of the show? If I get in the car and start driving before the program ends, huh?
1 minus x is between 5 and 15.
Right. So if so this is x, this is y, or possibly this is y and this is x. No, this is not possible, right? Because the show no, it is possible. Okay. This is 8:30. 8:30. The show starts here. This is the end time of the show, ending time of the show. Now, if the ending time of the show is after x, which is my start time, then I catch at least part of the show. Okay? In this case, I do not catch the part of the show. So basically, y minus x should be bigger than or equal to 0. Okay. But what do we know about y? Y is between, y is between 5 and 15. Okay. So let's draw this two-dimensional picture. This is y, this is x. Y is between 5 and 15. Okay. And x is between 0 to 30. And I want, so basically I'm here in this rectangle. Right? And this rectangle, let me draw this better. This is 5 to 15. Let me try to draw it sort of up to scale looking. This is x. X is between 0 to 30. And y, the ending time of the show, is between 5 to 15. So all possibilities are in this rectangle. Do you agree? All possibilities are in this rectangle. Is this my sample space? This is my sample space, omega. Does everybody agree? Because y lives between 5 and 15, x lives between 0 to 30. Okay, in this sample space, what is the event of interest? The event of interest is y minus x bigger than 0. What is y minus x bigger than 0? This is y equals x. This is the line y equals x. Y bigger than x is this part of this line. Okay? And its intersection with my sample space is this region. Okay? So how do I then find the probability? See, my sample space is a continuous sample space, and both x and y are uniformly distributed. So the xy pairs are uniformly distributed. Then the probability of this region, of the event A, let's call it event B, probability of the event B is the area of the red shaded region divided by the area of the rectangle. Right? Area of the rectangle. Okay? What is the area of the rectangle? This is 30. This is what? 10. 30 times 10. What is the area of this trapezoid? Let's see. What is this point? 5. Right? So this length is 5. What is this point? 15. So this is 15. Huh? This is 15. 15 plus 5, 20. Right? 20 times 10. Right? Excuse me? What? Okay, we'll do that. Wait. No, we don't. Okay, so I reused B as the event B, that is the event that I catch the show. Okay? And I also use this as this region, the name of this region. Yes, please. Okay. Excuse me, repeat again. X and Y. Okay, let's start again. Let's start again. Okay. X is my start time. X is my start time. Y is the time that the show ends. Okay? Where does X live? X lives from 0 to 30. And Y lives where? Y is uniform between 5 to 15. Y is uniform from 5 to 15. Okay? So the XY pairs are uniform in this rectangle. Yes, please. Because there are 30 minutes in this interval. I'm thinking in terms of minutes. There are 30 minutes in this interval. And my start time, I'm setting the origin to 0. I don't lose anything by doing that. Okay? My start time is between 0 and 30. The show ending time is between 5 and 15. So, since these are uniform and these are uniform, the pairs, XY pairs, are uniform in this region. Yes, please.
In this notation, you described X and Y as start time and end time of the show, and you reason that Y minus X is equal or...
Start time of driving. Okay? If this seems a little puzzling to you right now, don't worry too much, because this is just your first encounter with this type of thing. Let me finish the example, and I'm not really doing something rigorously in this example. Later on, we'll define random variables and probability distributions, which through that we'll be able to do this mathematically in a way that will be more clear to you. However, this is just an introduction to you for continuous sample spaces. The event of interest is this event. Let's call it B. The probability of B is the area shaded, let's call it shaded area, divided by the area of the sample space. Why? Because every point is equally likely, and the probability that a point falls in this region is proportional to the area of this region. Let's leave it at this for now, and we will revisit this when we define random variables. Let's see, what's the time? Okay, I have 7 more minutes. Let's move over to, we have a new very important definition coming up, which is conditional probability. Okay? So if you were even slightly confused by the previous example, please set it aside. Okay? Take a deep breath, although we don't have a lot of air left in this room. And, you know, focus for 5 minutes on something new. Okay? We're, you know, defining a new, we're making a new definition, which is conditional probability. Okay? Conditional probability. It's the probability of an event given that another event happened. Okay? The probability P A given B is the notation, and it means the probability of A given that B occurred. Okay? Here's how it's defined. Let A and B be 2 events where the probability of B is different from 0. The conditional probability PA given B of A given B is defined as the probability of A intersection B divided by the probability of B. This is just a definition. This is nothing that you can prove. It's just a definition. But I'll just draw a picture that sort of intuitively tells you that this definition makes sense. Okay, but there's nothing rigorous about the picture I'll draw. Okay, so this is event B, and this is event A. Okay? A priori means before anything happens, the probability of A is P of A. Now somebody told me that B happened. If B happened, then I know that I'm in B. The rest of the sample space, omega, is irrelevant now because B happened. B happened means we are in B. Okay? For example, the sample space was the numbers 1, 2, 3, 4, 5, 6. Okay? The outcomes of tossing a die. Okay? And somebody told me, okay, I tossed a die and the number I got is even. That's B. Now, what is the probability of A? Suppose A is, the number is between 1 and 3. Okay, 1, 2, 3. A is the event, that the outcome is 1 or 2 or 3. What is the probability, conditional probability of A? Prior to this information about evenness, the probability of A was 1/2, right? 1, 2, 3. The probability of getting 1 or 2 or 3 is 3/6, which is 1/2. Okay? Now, if they told me that the outcome is even, then some of the outcomes are ruled out. What is ruled out? 1 is ruled out. 3 is ruled out. The only possible outcome that can have happened, is this intersection, which is 2. Okay? Now the conditional probability of 2, how would you guess that should be? What would you guess the conditional probability of A to be, given B happened? Well, in B we have 2, 4, and 6. In the intersection we just have 2. So 1/3. A given B would be 1/3. Okay? This is not a proof. This is just an intuitive argument showing that the definition makes sense. Because if you actually apply the definition, that's the probability of A intersection B divided by the probability of B. What is A intersection B? A intersection B is just the outcome 2. This is the probability of the outcome 2. What is the probability of getting an even number? 1/2. So it's 1/6 over 1/2, which is 1/3. Okay? So the definition, at least, makes sense, but this is a definition. Okay. So I think it's a good time to take a break, 10 minutes break, and now we'll continue.